200 million years ago, all the land on Earth was joined together as one vast supercontinent, Pangea. But how did it form, and why did it eventually break apart into the continents we know today? Together we'll uncover the story of Earth's greatest assembly. If you enjoy discoveries like this, please like, subscribe and share. Thank you for watching. Now let's begin. Long before the Earth hosts a single unified landmass, its surface is divided into drifting fragments, each slowly moving over the upper mantle. These pieces are known as tectonic plates, and some of them carry the continents. In the deep time of the late Precambrian and early Paleozoic, there is no Pangea. Instead, the land is scattered. The continents, as we know them today, do not yet exist. What exists are ancient cratons, stable rigid cores of continental rock that date back billions of years. These cratons are surrounded by belts of younger, more deformable rocks. They act like floating islands across the global ocean, separated by vast basins of oceanic crust. Among them are Laurentia, which includes what will become North America and Greenland, Baltica, which holds the heart of modern northern Europe, Siberia, which sits apart in the north, and a collection of southern fragments, some of which will eventually become the vast Gondwana. Gondwana itself is not yet whole. It is slowly coalescing from smaller continental blocks, such as the Congo, Craton Kalahari, Craton São Francisco, Amazonia, India, and others. The movement of these fragments is driven by mantle convection. Beneath the crust, hot material rises from deep within the Earth, cools as it approaches the surface and sinks again. This cycle over immense spans of time creates slow, horizontal motion in the overlying plates. The plates move only a few centimeters each year, roughly the rate at which fingernails grow. But over tens or hundreds of millions of years, these subtle movements change the face of the planet. Continents that begin thousands of kilometers apart gradually drift toward one another. Oceans between them shrink. New ocean crust forms at mid-ocean ridges where magma rises and solidifies. Meanwhile, older ocean crust sinks back into the mantle at subduction zones, which are long, deep trenches at the edges of plates. This cycle, birth at ridges, death at trenches, is central to the plate tectonic engine. One such ancient ocean is the Iapetus Ocean. It lies between Laurentia Baltica and Avalonia, and it stretches wide during the early Paleozoic. Over time, this ocean begins to close. As the plates carrying Baltica and Avalonia move toward Laurentia, the ocean crust is slowly pulled down into the mantle. Sediments accumulate along the edges of the approaching continents. Volcanic arcs form above the subduction zones. These processes are recorded in belts of volcanic rock and metamorphic zones that still exist today. When continents collide, neither plate is easily subducted because both are buoyant and thick. Instead, the crust crumples and folds. Mountain belts rise where the land is pushed together. This happens first during the Caledonian orogeny, a mountain-building event that affects what is now Scandinavia, the British Isles and eastern North America. At nearly the same time in what is now the eastern United States, the Acadian orogeny results from similar collisions. Meanwhile, in the southern hemisphere, Gondwana begins its slow assembly. Smaller cratons are drawn together. This process, though less well preserved than in the north, is still visible in the rock record. In Brazil and Western Africa, geologists find similar mineral belts matching glacial deposits and shared deformation patterns. These are interpreted as evidence of suturing between ancient land fragments. The process is neither rapid nor straightforward. Some blocks accrete quietly, while others bring with them volcanic arcs or oceanic plateaus. These exotic terrains do not originate nearby. They may have formed thousands of kilometers away before traveling across the ocean and attaching to the growing continent. The resulting crust is patchwork composed of rocks with different origins, histories and magnetic orientations. These differences help modern scientists unravel where the pieces came from. The idea that continents move was once controversial. For much of the 20th century, it was debated whether the similarities between fossil assemblages and mountain belts across continents were due to ancient land bridges or to drifting continents. The eventual acceptance of plate tectonics in the 1960s confirmed that continents do indeed move, and that the similarities result from earlier connections. Paleomagnetic data provide a key line of evidence. When volcanic or sedimentary rocks form iron minerals within them align with Earth's magnetic field. As the rock hardens, this orientation becomes fixed. By measuring the direction and inclination of this magnetism in ancient rocks, scientists can determine the latitude at which the rock formed. When rocks from different continents show the same paleolatitude and orientation, it suggests they were once near each other. Fossils too serve as markers of past geography. In the rocks of South America, Africa, India and Australia, paleontologists find identical species of ancient plants like Glossopteris and animals such as early reptiles and amphibians. These organisms could not have crossed wide oceans. Their distribution makes sense only if the continents were once joined. Similarly, glacial striations, long parallel grooves carved by ice sheets match across southern continents, pointing in directions that only make sense if the landmasses were once connected in a southern polar configuration. By the end of the Cambrian and into the Ordovician, the pieces are slowly converging. Laurussia, also called Euramerica, begins to take shape from the union of Laurentia Baltica and Avalonia. It sits closer to the equator and forms one of the core northern continents. Gondwana farther south stretches across the southern pole and into the temperate zones. Though they are still separated by shrinking oceans, the continents are on a course toward union. Each step, each collision, each subduction, zone each mountain belt brings Earth closer to the formation of a single supercontinent. Pangea is not yet formed, but the process has begun. The Earth's surface moves slowly, silently, invisibly on human timescales, but in deep time the continents drift and collide like icebergs on a dark sea. Their paths preserved in stone and fossil reveal the patient logic of tectonic motion. This is the long prelude to the birth of Pangea. The path toward Pangea continues as Laurentia Baltica and Avalonia close the remaining distance between them. These continental blocks, once separated by the wide Iapetus Ocean, now move slowly toward collision. The Caledonian orogeny intensifies as Baltica converges with Laurentia, creating a chain of mountains that will one day form the ancient roots of ranges in Scandinavia, Scotland and eastern Greenland. Thick slabs of crust buckle and rise. Rocks are buried deep-heated and transformed by pressure. At the same time, Avalonia, a smaller microcontinent, approaches from the south. Its arrival marks the final closure of the Iapetus Ocean. The sea that once separated these landmasses disappears, replaced by folded rocks, metamorphic belts, and the traces of former oceanic sediments trapped between the colliding masses. These mountain-building events do not occur all at once. Instead, they happen in a slow sequence, taking tens of millions of years. Sediments once deposited along the margins of the ocean are scraped up and thrust onto the continental edges. Deep-sea rocks now raised high above sea level remain as evidence of these past collisions. With these northern blocks now sutured together, a new composite continent forms. Geologists refer to it as Laurussia or Euramerica. It straddles the equator, stretching from what is now North America through northern Europe. This united landmass becomes the central core of the eventual supercontinent, while Laurussia holds steady movement continues elsewhere. In the southern hemisphere, Gondwana grows more complete. The collisions that build Gondwana are complex and involve the joining of cratons such as the Amazonian San Francisco Congo Kalahari and Mawson cratons. Each carries with it a separate history of volcanism, sedimentation, and deformation. These histories are now written side by side in the geological record. Orogenic belts crisscross the terrain running through parts of what are now Brazil, Africa, India, and Australia. The Brazilian and African shields show mirror image patterns of magnetic orientation and metamorphic belts, providing further evidence of their former connection. Between Laurussia and Gondwana lies the Rheic Ocean. This ocean is younger than the Iapetus, and it separates the new northern continent from the vast and growing Gondwanan supercontinent. Subduction begins beneath Laurussia's southern margin, gradually pulling Avalonia and other microcontinents toward it. The ocean floor descends beneath the continental edge, forming volcanic arcs and deep trenches. As the Rheic Ocean narrows, the stage is set for the next great collision. In the late Devonian, and into the Carboniferous terrains and smaller continental fragments are caught in this convergence zone. Some are trapped and accreted along the edge of Laurussia. Others are carried along with oceanic plates and eventually slammed into the northern margin of Gondwana. With each movement, the Earth's lithosphere is reshaped. Magmatic activity increases near subduction zones. Crust thickens. Oceanic basins shrink and vanish. This long sequence of collisions and closures leads to the final suturing of Laurussia and Gondwana. The resulting event, known as the Alleghanian orogeny in North America and the Variscan orogeny in Europe, produces some of the most significant mountain belts of the Paleozoic era. These belts, which once rival the Himalayas in scale, form along what is now the eastern United States, the British Isles, and parts of mainland Europe. Thick wedges of folded and faulted rock are created as one continent overrides another. Sediments that had collected in foreland basins are squeezed, raised, and deformed. Volcanic activity and regional metamorphism mark the zones of intense crustal disturbance. This final collision between Laurussia and Gondwana eliminates the Rheic Ocean and completes the assembly of the supercontinent Pangea. Pangea now stretches across nearly one-third of the planet's surface. Its core lies near the equator, but its vast expanse reaches from the northern to the southern polar regions. Its formation creates a massive continuous landmass surrounded by a global ocean called Panthalassa. Within its margins lie smaller seas, including the Paleotethys, which hugs its eastern edge. The union of the continents locks together different biomes and geologic histories. Rocks from once separate continents now lie side by side, and their contrast reveal the nature of their separate origins. In some regions, ancient basement rocks remain exposed, providing a glimpse into deep time. In others, younger sedimentary basins begin to form atop the newly formed landmass. The process of continental collision not only builds mountains, but also influences the patterns of erosion and sedimentation. Rivers begin to flow from the elevated highlands of the interior toward the surrounding lowlands and coastal regions. Sediment derived from weathered mountain belts fills basins and forms thick layers of sandstone, shale, and limestone. These strata, deposited in vast sheets, preserve the remains of ancient ecosystems. Fossils of plants, amphibians, insects, and marine organisms accumulate in these layers, capturing snapshots of life on and around Pangea. The widespread similarity of fossils across regions now separated by oceans is one of the strongest lines of evidence that Pangea once existed. Glossopteris, an extinct genus of seed fern, is found in South America, Africa, Antarctica, and Australia. These plants could not have crossed vast oceans. Their distribution is only explained by a former land connection. As Pangea stabilizes, the internal dynamics of the supercontinent continue to evolve. The lithosphere beneath it responds to the immense weight and pressure of the overlying crust. Mantle heat builds up beneath the insulated interior. Unlike smaller continents surrounded by oceans, Pangea's sheer size alters the way heat escapes from Earth's interior. This affects the thermal structure of the mantle and contributes to changes in tectonic behavior over time. Subduction zones once located along the margins of individual continents now ring the outside of the supercontinent. These subduction zones continue to consume oceanic crust and create new mountain chains along Pangea's periphery. In the deep crust and mantle below, the accumulated energy of past collisions remains. The sutures between once separate continents remain zones of weakness. Though the continents are now joined, they are not fused seamlessly. These inherited structures will eventually guide the breakup of Pangea. But for now, the world is unified. A single supercontinent spans pole to pole. Ocean currents flow around its margins. Climate patterns begin to form across its vast interior. The stage is set not only for new geological developments, but for the spread of terrestrial life across connected landscapes. Pangea stands as the most complete example of continental assembly in the geological record, a landmark in the long story of plate tectonics. At the heart of the newly assembled supercontinent, a series of vast mountain belts rise along the collision zones that once divided separate landmasses. These mountain ranges are not built in a single moment, but form gradually over tens of millions of years, as tectonic plates grind together and crust is pushed upward. In what is now eastern North America, the Alleghenian orogeny creates a chain of mountains stretching from what will become the southern Appalachian region, northward into present-day Newfoundland, and across into the British Isles. These mountains result from the final collision between La Russia and Gondwana, and their roots remain visible today in the deeply metamorphosed rocks and folded sediments that still line the eastern seaboard. To the east, the Variscan orogeny produces mountain belts across parts of modern-day France, Germany, and the Iberian Peninsula, while the Hercynian belt spans Central Europe, revealing another zone of deep crustal disturbance. These ranges are accompanied by foreland basins where thick packages of sediment accumulate as material erodes from the rising highlands. Rivers carry the debris downslope, depositing sands and muds that eventually harden into sedimentary rock. In some areas, these basins preserve fossils of early terrestrial life plants, insects and amphibians captured in the quiet intervals between pulses of mountain building. The scale of these mountains is enormous. Estimates suggest that they may have reached elevations comparable to the modern Himalayas. Deep within their cores, rocks are subjected to pressures and temperatures so high that they recrystallize into new minerals. Foliated metamorphic rocks such as schist and gneiss develop in zones of intense deformation. Granitic intrusions rise from below as molten rock finds its way into the fractured crust. The result is a complex network of intrusive and metamorphic structures that form the deep foundations of the continental crust. These mountain belts stretch thousands of kilometers across the core of Pangea, forming a continuous topographic divide from the interior of what is now North America through Central Europe and into northwestern Africa. From a geologic perspective, this central chain marks the suture, the scar where the separate plates were stitched together. Around these highlands, a variety of topographic and depositional features begin to develop. Some regions form large plateaus where a thick crust is uplifted but not heavily deformed. Other areas sink slightly under the weight of newly formed mountains, creating elongated basins that slowly fill with sediment. These regions, known as molasse basins, receive thick successions of terrestrial deposits, conglomerates from high-energy streams, sandstones from braided rivers, and fine mudstones from floodplains. These deposits are interbedded with layers of coal formed from the compression of dense vegetation in wet, swampy lowlands. The Carboniferous period, which overlaps with the assembly of Pangea, becomes one of the most prolific coal-forming intervals in Earth's history. In what is now Western Europe, Eastern North America, and parts of Asia, vast tropical wetlands spread across the four land basins fed by seasonal rainfall and sustained by warm equatorial temperatures. The coal beds they leave behind serve as geological markers for the supercontinent's interior environment. The interior of Pangea is immense, and its geography affects more than just topography. As the continent grows in size, its centre becomes increasingly isolated from the influence of oceanic moisture. Modern continents benefit from the moderating effects of nearby oceans, which regulate temperature and bring precipitation. But in the case of Pangea, the sheer distance from coast to interior means that the central regions begin to experience strong seasonal contrasts. Summers become extremely hot while winters turn dry and cold. Precipitation declines significantly in the inner parts of the continent. These conditions favour the development of arid and semi-arid climates. Wind-blown sediments or aeolian deposits become more common in the geologic record. Cross-bedded sandstones formed from ancient dunes indicate the presence of large desert systems spreading across the interior of the supercontinent. Despite this aridity, weathering in the mountain regions continues. Rainfall, though seasonal, contributes to erosion along the flanks of the highlands. Rivers carve valleys, transport sediments, and feed delta systems along the continental margins. Over time, the combination of erosion and subsidence creates complex sedimentary packages that record both the uplift of mountains and the drying of basins. In some areas, evaporate minerals such as gypsum and halite begin to accumulate, especially in isolated inland basins where water evaporates faster than it can be replenished. These minerals form in hot, dry environments and are often associated with periods of continental interior desiccation. In parallel with the mountain formation and basin development, the movement of the supercontinent has important consequences for Earth's global circulation. Pangea's position across the equator and its connection from pole to pole affect atmospheric and oceanic patterns. With most of the landmass united into a single block, air circulation becomes more continental and monsoonal in character. Large pressure gradients form between the hot-dry interiors and the cooler, moist margins. These gradients drive strong seasonal winds. The distribution of precipitation becomes highly asymmetrical, with heavy seasonal rains falling near coastal regions and extended dry seasons dominating inland. This climate system leaves behind geologic indicators such as red beds, oxidized iron-rich sediments that point to prolonged exposure to the atmosphere in semi-arid conditions. In addition, paleosols or ancient soil horizons show features like calcrete nodules and desiccation cracks, further confirming the harsh seasonal conditions in the heart of Pangea. The combination of high elevation interior dryness and extreme seasonal shifts creates a unique landscape unlike anything found on modern Earth. It is a continent of contrast-high mountain belts, bordered by eroded basins, swampy lowlands transitioning into desert dunes, tropical coal forests near the coasts giving way to sun-baked plateaus far inland. Fossil evidence supports this environmental gradient. In the Carboniferous and early Permian flora in the wetter regions includes dense forests of club mosses, horsetails and seed ferns, while farther inland plants adapted to drier climates begin to dominate, including early conifers and other drought-resistant forms. Animal life adjusts accordingly. Amphibians thrive in humid lowlands while early reptiles better suited to arid conditions expand into the more open interior landscapes. Geologically, the legacy of these environments is recorded in the rocks that remain today. The Appalachian Mountains, the Variscan Belt, the Ural Mountains, and associated structures all trace their origins to this great continental union. Though erosion has reduced their heights, their roots still lie buried in the crust, preserved as zones of metamorphic and igneous rock. the surrounding sedimentary basins continue to yield fossils, coal, and other mineral resources that tell the story of an ancient supercontinent shaped by tectonic forces, climate systems, and the slow processes of erosion and deposition. Far from the mountainous interior of Pangea, the continent's edges offer a striking contrast. Along its vast margins, the land meets the sea in low-lying coastal plains, shallow marine shelves, and broad deltas that mark the transition from continental crust to oceanic basins. These coastal regions, unlike the highlands, are dynamic interfaces between land and water, shaped by tides, waves, and longshore currents. In many places, the crust near the edges of the supercontinent has thinned and sagged under its own weight, forming broad marginal basins that gradually fill with sediments. These sediments arrive from rivers that drain the continent's interior, carrying with them eroded material from mountain belts and upland plateaus. As they reach the coast, the rivers slow, depositing sand, silt, and clay in layers that build outward into the sea. These coastal sedimentary systems preserve a complex and detailed record of the changing environments at the edge of Pangea. The epicontinental seas that cover these lowlands are shallow, warm, and often expansive. Unlike the deep ocean, where light barely penetrates and pressure increases rapidly with depth, these shallow seas are sunlit and relatively stable. Their waters are rich in nutrients, oxygen, and life. Coral reefs, sponge gardens, and algal mats thrive in the clear waters near carbonate platforms. Farther offshore, deeper but still shallow settings support diverse marine ecosystems filled with brachiopods, ammonoids, crinoids, and bony fishes. In these environments, biological productivity is high, and the remains of organisms accumulate on the seafloor, eventually becoming part of the sedimentary record. Limestone and dolostone form from the buildup of calcium carbonate skeletons, while black shales and organic-rich mudstones indicate times and places where oxygen becomes limited and organic material is preserved. These rocks are crucial to understanding the paleoenvironment and are later important as source rocks in the formation of fossil fuels. Along Pangea's eastern margins, where the Paleotethys Ocean laps against the continent, wide tropical shelves stretch for hundreds of kilometers. These shelves are interrupted by carbonate platforms and reef systems that resemble modern analogues found in the Caribbean and Western Pacific. However, they are much more extensive, shaped by the long stability of the passive continental margin. In other areas, especially where tectonic forces continue to operate, active margins develop. Here, oceanic crust is subducted beneath the continent, creating trenches, volcanic arcs, and narrow forearc basins. These settings give rise to different sedimentary patterns, including turbidites, underwater landslide deposits interbedded with volcanic ash and debris flows. The result is a rich and varied stratigraphic record that reflects both the quiet accumulation of sediments in broad seas and the violent episodes of tectonic disruption and volcanism. The climate along Pangea's coasts is influenced by both latitude and proximity to the ocean. In equatorial regions, warm temperatures and high humidity promote tropical conditions. Rainfall is frequent and intense, fueling rivers and deltas. Mangrove-like wetlands and dense vegetation line estuaries, while freshwater swamps and floodplains extend inland. In these environments, large coal-forming peat swamps develop, especially during periods when sea level remains relatively stable. Farther north and south, the coasts shift into temperate and even arid conditions depending on their position relative to the supercontinent's broad climate belts. Seasonal variations in wind and precipitation lead to complex sedimentation patterns with alternating wet and dry intervals recorded in varved clays, evaporate layers, and paleosol horizons. These coastal environments serve not only as depositional systems, but also as critical habitats and dispersal corridors for life. During the late Paleozoic and early Mesozoic, terrestrial organisms begin to diversify rapidly. The connected landmass of Pangea allows for the migration of plants and animals across vast distances. Along coastal plains and floodplains, large herbivorous reptiles graze on low-growing vegetation, while carnivorous forms hunt in river valleys and swamp margins. Amphibians thrive in moist areas, taking advantage of the abundant freshwater systems, while early archosaurs and therapsids spread into drier upland zones. Footprints left in soft mud later harden into fossilized trackways, capturing the daily movement of these ancient creatures. Fossilized bones, teeth, and even skin impressions accumulate in channel fills and overbank deposits, preserving a detailed biological record. Marine life continues to evolve in tandem. The seas along Pangea's edges host diverse communities of invertebrates and vertebrates. Bivalves, gastropods, and echinoderms are abundant on the seafloor, while sharks, ray-finned fishes, and early marine reptiles swim in the open water. Changes in sea level driven by both tectonic and glacial influences create transgressive regressive sequences in the stratigraphic record. During sea level rise, marine waters advance over the land, depositing shallow marine sediments atop terrestrial ones. When sea level falls, rivers rework the sediments and cut deep channels into the former seafloor. These cyclic sequences are recorded in outcrops around the world, allowing geologists to correlate distant regions and reconstruct the shifting shorelines of the ancient supercontinent. The sedimentary rocks formed in these coastal and shelf environments become essential archives of geologic time. They capture not only the physical processes of erosion, transport, and deposition, but also the chemical and biological conditions of ancient Earth. Isotopic signatures within carbonate minerals reveal changes in ocean chemistry and atmospheric carbon levels. Fossil assemblages indicate shifts in temperature, salinity, and habitat range. Layers of volcanic ash preserved as bentonite provide precise time markers through radiometric dating. These clues, when pieced together, create a coherent picture of life and landscape at the edges of Pangea. Importantly, the coastal zones also reflect the first signs of stress within the supercontinent. As the interior grows increasingly arid and tectonically stable, the margins remain zones of change. Thermal subsidence, sediment loading, and inherited weaknesses in the crust contribute to stretching and thinning of the lithosphere in some regions. This stretching sets the stage for future rifting. Even as Pangea reaches its most unified form, the seeds of its breakup are already being planted along its edges. Fault zones develop. Magmatic intrusions rise along deep fractures. Rift valleys begin to open, though slowly and often unnoticed in the rock record until much later. These early signs are subtle, but they are persistent. The same margins that once welcomed the joining of continents will in time become the sites of separation. For now, however, Pangea remains whole. Its coasts are wide and varied, shaped by the interplay of land and sea sediment and salt life and time. From the highland rivers that carve through the interior to the deltic lobes that build outward into shallow seas, the edge of the supercontinent is alive with change. It is here that Earth's geologic processes are most visible, layer by layer, tide by tide, season by season. In the stillness of stone, these coastal regions quietly record the movements of a planet that never truly rests. Across the great expanse of Pangea's connected land, the removal of ocean barriers allows life to move in new directions. The physical union of continents reshapes ecosystems on a continental scale. Land animals no longer face deep seas between regions. Instead, they roam freely across vast interior plains, along river valleys, through coastal lowlands, and across arid plateaus. The Permian period, which follows the Carboniferous, becomes a time of extensive faunal interchange and diversification. Reptiles in particular spread widely. Unlike amphibians, which remain dependent on moist environments for reproduction, reptiles lay shelled eggs that resist desiccation. This evolutionary innovation allows them to colonize the drier uplands and interior deserts of Pangea. Their success is reflected in the fossil record. Different groups of early reptiles, parareptiles, synapsids, diapsids diversify and spread across the continent. Some evolve into large herbivores with barrel-shaped bodies suited to digesting tough vegetation, while others become agile predators adapted for speed and endurance on open terrain. Plant life also changes. In the wetter regions along the coast, seed ferns, horsetails, and club mosses continue to flourish in swampy lowlands. These areas remain dominated by dense vegetation thick with ground cover and canopy. But farther inland, the vegetation shifts toward more drought-resistant types. Gymnosperms, including conifers, begin to dominate the drier upland environments. Their needle-like leaves reduce water loss, allowing them to thrive in semi-arid zones, where seasonal rainfall is brief and unpredictable. These plants spread across the interior of Pangea, where desertification intensifies as the distance from the coasts increases. The result is a patchwork of habitats, wetlands near the margins, seasonal woodlands, farther inland, and arid shrublands and dune fields in the continental heart. Each supports its own suite of life, yet the lack of oceanic barriers means species can migrate, adapt, and radiate over a unified landscape. Fossil evidence supports these patterns. Similar reptile species are found in Permian-age rocks across what are now North America, Europe, South America, and Africa. One example is Mesosaurus, an aquatic reptile whose remains appear in both Brazil and southwestern Africa. Another is Lystrosaurus, a robust herbivore whose fossils are common across Antarctica, India, and southern Africa. These wide distributions make sense only if the continents were once connected. The same applies to plant fossils. Species such as Glossopteris, a seed fern with distinctive tongue-shaped leaves, appear across Gondwana in deposits that also contain coal, indicating that these plants thrived in broad forested wetlands near the ancient South Pole. This shared biological record allows paleontologists to reconstruct past ecosystems and trace the movement of life across the supercontinent. These dispersal patterns are not random. Geography, climate, and elevation all influence where species can travel and establish populations. Mountain belts serve as partial barriers, directing the flow of rivers and creating rain shadows that further shape climate zones. In the interior basins, isolated by arid uplands and long distances, local adaptation can lead to endemism. Some species evolve unique traits suited to narrow ecological niches. Others disappear entirely in periods of climatic stress or environmental change. The fossil record includes numerous extinction events, many localized but some widespread. These extinctions are preserved in the abrupt disappearance of species from sedimentary layers, sometimes replaced by new forms that appear suddenly and expand rapidly. In the oceans surrounding Pangea, marine life continues to evolve in distinct biogeographic provinces. The isolation of certain seaways and the geometry of the supercontinent's margins create separate marine realms. In the Tethys region, warm tropical waters host diverse reef ecosystems filled with sponges, brachiopods, and ammonoids. In contrast, the Panthalastic Ocean, which dominates the globe, supports deep-water communities with different assemblages. These variations result not just from temperature and depth, but also from salinity, nutrient availability, and ocean circulation. Fossils from these different regions allow geologists to identify ancient continental positions and to track the opening and closing of marine gateways. In particular, the orientation of coral reefs and the presence of particular species of conodonts, small tooth-like microfossils, help map the ancient coastlines of Pangea and its neighbouring basins. Migration corridors for marine species also exist along continental shelves and through narrow straits. Changes in sea level often linked to glaciation and tectonic activity expand or contract these routes. When sea level falls, coastal habitats shrink, and shallow marine species may become isolated or extinct. When sea level rises again, new pathways open, allowing recolonization and mixing of faunal groups. These sea level changes are reflected in the geologic record as transgressive and regressive sequences, with marine sediments advancing over terrestrial ones and then retreating as land emerges again. The patterns are global, allowing for the correlation of rock layers across different continents and the reconstruction of sea level curves through deep time. Not all dispersals across Pangea occur easily. Some environments, particularly hyper-arid deserts, serve as effective barriers. Sand seas or ergs cover large portions of the supercontinent's interior. These dune fields are composed of fine, well-sorted quartz grains deposited by prevailing winds. Cross-bedding in ancient sandstones reveals the direction and strength of these wind systems. Few animals can survive in these regions. Water is scarce. Vegetation is sparse and temperatures fluctuate widely between day and night. Still, some organisms adapt. Burrowing reptiles, insectivorous predators, and drought-tolerant plants find ways to persist in the margins of these harsh environments. Their presence is rare in the fossil record but significant. It points to evolutionary resilience and the gradual spread of life into even the most extreme habitats. The connections across Pangea are not only biological but also geological. Mineral belts, fault zones, and rock formations that cross current continental boundaries serve as further proof of ancient unity. The Appalachian Mountains in eastern North America align with the Caledonides in Scotland and Scandinavia. Matching structural trends, metamorphic histories, and isotopic ages confirm their shared origin in a once continuous orogenic belt. Similarly, the Karoo Basin in southern Africa, the Paraná Basin in South America, and parts of the Indian subcontinent share sedimentary successions and fossil assemblages that reflect common depositional settings during the late Paleozoic. These matches are so precise that geologists can trace continuous layers of sandstone coal and volcanic ash across what are now separated continents. As more fossil and rock data accumulate, the picture of Pangea becomes increasingly detailed. It is a world where life moves in patterns shaped by land and sea, where mountains, deserts, forests, and deltas define both the possibilities and limits of movement. The unification of the continents creates both opportunities for connection and challenges of isolation. It is not a static world, but one in motion tectonically, climatically, and biologically. In every corner of the supercontinent, life responds to these changes in different ways. Some species expand their ranges and adapt. Others fade from the record. All leave behind traces preserved in stone awaiting discovery. As Pangea reaches its greatest extent, the climate across the supercontinent becomes increasingly extreme. With so much landmass concentrated into a single block, the atmospheric and hydrologic cycles behave differently than they do on a planet with dispersed continents. The interiors of Pangea lie far from the moderating influence of the oceans, making temperatures more variable and precipitation patterns less predictable. In modern times, ocean proximity helps regulate climate-buffering summer heat and winter cold, while supplying steady moisture to nearby regions. But in Pangea's interior, thousands of kilometers from any coast, these stabilizing effects are absent. The result is a continental climate marked by intense heat during summer cold winters and prolonged dry periods. Geologic and fossil evidence confirms these extremes. Ancient soils preserved in the rock record known as paleosols reveal alternating wet and dry conditions, with features such as calcrete nodules, desiccation cracks, and oxidized horizons that indicate long periods of aridity and strong seasonal cycles. The climate is further shaped by the position of the supercontinent across the equator. Pangea stretches from the northern polar regions to the southern polar cap, crossing a wide range of latitudes. This arrangement affects wind patterns and monsoonal circulation. During the Permian period, the equatorial region of Pangea experiences intense heating, especially during the summer months. Warm air rises over the interior, creating a powerful low-pressure zone that draws moist air inward from the surrounding seas. This produces a seasonal monsoon system in which heavy rains fall during part of the year, followed by long dry seasons. In some areas, the monsoon brings temporary relief to the dry lands feeding rivers and supporting seasonal vegetation. In other regions, especially those in the central and western interiors, the rainfall is insufficient and deserts dominate the landscape. The geologic record preserves the footprints of these ancient climatic systems. Red-bed sedimentary rocks stained by iron oxides accumulate across vast stretches of Pangea. These rocks form in semi-arid environments where rainfall is episodic, and the oxidation of iron in soils and sediments creates their characteristic coloration. They are often associated with river deposits, floodplain muds, and Aeolian sands. Large-scale cross-bedding within the sandstones indicates the presence of active dune fields shaped by strong, persistent winds. In some places, wind-blown sediments form thick sequences that extend for hundreds of meters, marking the development of ancient desert systems. These arid zones are not limited to a single region, but occur across what are now parts of North America, North Africa, the Middle East and Central Asia, showing the widespread influence of Pangea's interior climate. Despite the harshness of the interior, life continues to adapt. The development of the amniotic egg already established in earlier reptiles becomes increasingly important. With a protective shell and internal membranes, these eggs allow embryos to develop on land without dependence on water bodies. This innovation enables reptiles to colonize dry environments more effectively than amphibians. Fossil trackways, bone beds, and occasional articulated skeletons reveal the presence of diverse reptilian faunas across arid and semi-arid regions. Some species, such as early therapsids, mammal-like reptiles, begin to show advanced adaptations, including differentiated teeth, sprawling to semi-erect limbs, and more efficient breathing mechanisms. These animals become dominant in many of the upland and plateau regions where water sources are scarce and vegetation is limited. Plants evolve in parallel with these challenges. Gymnosperms, including seed ferns, conifers, and ginkgo phytes, expand across the drier regions. Unlike the spore-bearing plants of earlier periods, gymnosperms produce seeds that can remain dormant during unfavorable conditions and germinate when moisture becomes available. Their woody tissues allow them to withstand high winds and dry soils. In many parts of Pangea, conifer forests begin to replace the wetter, coal-forming swamps of the Carboniferous. These forests occupy upland areas and form the backbone of terrestrial ecosystems, providing food and shelter for a growing diversity of reptiles, insects, and other land-dwelling organisms. The transition from the Carboniferous to the Permian also brings changes in atmospheric composition. During the Carboniferous, oxygen levels had reached unusually high levels, likely due to the extensive burial of plant material in coal swamps, which removed carbon from the atmosphere and allowed oxygen to accumulate. This high oxygen environment supports large insects and high rates of wildfire. But as the coal swamps recede and arid environments expand, the burial of organic carbon decreases. As a result, oxygen levels fall and the atmosphere becomes drier and less supportive of giant arthropods. The fossil record shows a reduction in insect size and diversity, as well as an increase in fire-resistant and drought-tolerant plant forms. Charcoal layers formed from ancient wildfires provide further evidence of fluctuating atmospheric oxygen and changing vegetation cover. These atmospheric changes do not happen in isolation. They are linked to tectonic processes that continue to shape Pangea from below. The supercontinent sits atop a complex network of lithospheric plates and mantle convection cells. As the thick continental crust insulates the mantle beneath it, heat builds up over time. This heat accumulation causes thermal doming in certain regions where the crust begins to rise and stretch. Though not yet breaking apart, these zones of weakness mark the early signs of future rifting. One such area develops along what will later become the central Atlantic margin. Here, subtle extension begins to form fault zones and intrusions of basaltic magma, though these processes remain limited and mostly confined to the lower crust and upper mantle. Elsewhere, tectonic compression persists along Pangea's active margins. In the west, subduction continues along what is now the western coast of North and South America. Volcanic arcs and accretionary wedges grow as oceanic crust is pushed beneath the continental edges. These zones of subduction not only create new mountain belts, but also influence regional climate and ocean chemistry. Volcanic emissions release carbon dioxide and sulfur compounds into the atmosphere, which may contribute to long-term changes in temperature and precipitation. Some of these volcanic events are large enough to leave global signals, including short-term cooling from sulfur aerosols and longer-term warming from greenhouse gases. Despite its outward appearance of stability, Pangea remains geologically dynamic. The thick crust flexes, erodes, and responds to deep internal pressures. Sediment continues to accumulate in interior basins where layers of sandstone shale and evaporate minerals build up over time. These basins act as geological archives, preserving not only the physical products of erosion, but also the chemical signatures of the ancient atmosphere and hydrosphere. Isotopic ratios of carbon, sulfur, and oxygen in sedimentary rocks help reconstruct fluctuations in temperature, ocean salinity, and atmospheric composition. These geochemical records provide insights into how life and climate responded to the gradual but persistent changes that shaped Pangea's interior. Toward the close of the Permian, signs of ecological stress begin to appear. Fossil assemblages show reduced diversity in many regions. Extinctions increase, especially among marine organisms sensitive to temperature, salinity, or oxygen levels. In the terrestrial realm, faunal turnovers become more common, with older groups replaced by more drought-tolerant and efficient species. Though Pangea remains intact, its internal systems are beginning to feel the strain of prolonged environmental pressure. These changes mark the beginning of a profound shift, one that will eventually lead to the greatest extinction event in Earth's history. But for now, the supercontinent endures, stretched from pole to pole, holding within its boundaries a world shaped by dryness, heat, and the slow force of time. As the Permian period comes to a close, Pangea begins to show signs of deep internal stress. Though the supercontinent remains intact, the forces that once brought it together now begin to pull it apart. These forces originate far below the surface in the convecting mantle. Over time, as the massive landmass continues to insulate the underlying mantle, heat accumulates and creates thermal anomalies beneath the crust. This rising heat causes the lithosphere to expand and weaken, leading to the slow development of doming and rifting in several key regions. While no single event marks the beginning of Pangea's breakup, the early stages unfold gradually, with subtle shifts in the crust and localized volcanic activity that hint at the tectonic changes to come. One of the earliest indicators of this growing instability appears along the interior of what is now eastern North America and northwestern Africa. This region, once the site of continental collision during the assembly of Pangea, begins to undergo extensional forces. Ancient suture zones where separate landmasses had once fused together act as zones of weakness. As tension increases, the crust starts to stretch and thin. In some areas, rift valleys begin to form. These are long, narrow depressions bounded by faults where the land has sunk between diverging blocks. Within these rift basins, erosion from surrounding highlands fills the depressions with coarse sediments, including conglomerates and sandstones. In time, these sediments will become the earlier stratigraphic record of Pangea's fragmentation. As rifting progresses, magma begins to rise from the mantle into these areas of thinning crust. Though still limited in scope, this magmatism produces dikes and sills, sheet-like intrusions of igneous rock that cut through or lie between layers of sedimentary strata. In some places, volcanic eruptions reach the surface, spreading basaltic lava over the rift floor. These early magmatic events mark the beginning of a long sequence of geological processes that will eventually open new ocean basins. At this stage, however, the rifts remain mostly continental, and no new oceanic crust has formed. Still, the pattern is clear: the supercontinent is starting to fragment from the inside out. Elsewhere along the margins of Pangea, tectonic activity continues at subduction zones. Along what is now the western edge of North and South America, oceanic plates continue to descend beneath the continental lithosphere. This process maintains volcanic arcs and uplifts new mountain ranges. The Andes and ancestral Rockies are among the regions where compressional forces remain active. These subduction zones also serve as important sources of magmatic heat and contribute to the long-term cycling of materials between the crust and mantle. Over time, the buildup of magmatic pressure and tectonic deformation can influence stress fields across the entire continent, accelerating the onset of extension in adjacent areas. As rifting develops in certain regions, sedimentation patterns begin to change. Basins that had once received sediment from interior highlands now shift with new river systems draining into emerging rift valleys. In these basins, alternating layers of coarse and fine material accumulate, preserving clues to the changing landscape. Fossils within these sequences show a mixture of terrestrial and freshwater species, indicating the presence of lakes, floodplains, and ephemeral streams. In some rifts, evaporite minerals such as halite and gypsum form as shallow lakes dry out, leaving behind beds of salt. These evaporites will later play a key role in shaping structural traps for hydrocarbons, making them important in the geologic record for both scientific and economic reasons. Along the eastern margin of North America and the western margin of Africa, the rifting intensifies. The crust continues to thin, and the lithosphere begins to separate. At first, this results in the formation of narrow marine incursions where seawater floods into subsiding rift valleys. These proto-oceans are shallow and restricted, but gradually widen as extension proceeds. Eventually, the process of seafloor spreading begins. At mid-ocean ridges, new oceanic crust is generated as magma rises and solidifies. This marks the true beginning of the Atlantic Ocean. As seafloor spreading continues, the continents on either side drift apart, slowly separating the formerly joined lands of Laurentia and Gondwana. What was once a collision zone now becomes a passive continental margin. This separation has profound effects on regional and global climate. As the Atlantic Ocean begins to open, new ocean currents form, redistributing heat and moisture around the globe. The supercontinent, once wrapped by a single oceanic belt, is now divided by new marine pathways that allow for more complex circulation patterns. These changes affect wind systems, precipitation zones, and ocean productivity. In some areas, increased coastal upwelling brings nutrients to the surface, supporting rich marine life. In others, new oceanic barriers isolate populations of marine organisms, leading to evolutionary divergence and the formation of new species. As Pangea begins to fragment, the ecological consequences are significant. The great terrestrial corridors that once allowed animals and plants to migrate freely across the continent are gradually interrupted. Mountain building, rifting, and changing climates reshape the landscape into a mosaic of isolated regions. populations that were once part of broad ecosystems become separated by physical barriers or environmental shifts. These conditions foster speciation but also increase vulnerability. In the fossil record, we see the decline of some widespread species and the rise of more localized forms. The early Mesozoic becomes a time of both extinction and innovation, as organisms adapt to new environments shaped by tectonic change. Volcanic activity associated with rifting also plays a role in shaping the biosphere. As magma reaches the surface, it releases gases into the atmosphere, including carbon dioxide and sulfur dioxide. These gases can affect climate over both short and long timescales. In large volumes, carbon dioxide contributes to greenhouse warming, while sulfur aerosols can reflect sunlight and cause temporary cooling. These effects are recorded in geochemical markers within sedimentary rocks, including isotopic excursions that indicate shifts in global temperature and carbon cycling. In some cases, volcanic activity may have played a role in extinction events by altering climate-ocean chemistry or both. Despite the growing complexity of the landscape, the breakup of Pangea is not uniform or simultaneous. Different regions rift and drift at different rates. Some areas remain tectonically stable for tens of millions of years while others undergo rapid change. The process unfolds in stages with episodes of extension volcanism and seafloor spreading punctuated by periods of relative quiescence. Over time, the single landmass that was Pangea gives way to a series of drifting continents, each carrying with it fragments of the supercontinent's geological and biological history. What remains in the rock record are the scars of separation. Rift basins filled with sediment, intrusive dikes and sills, volcanic layers, and fault-bounded valleys all testify to the slow dismantling of Earth's greatest supercontinent. These features preserved in the crust across the globe are the evidence of a process still ongoing today. The continents continue to move, the oceans continue to open and close, and the surface of the Earth remains in motion. But in the slow rhythm of plate tectonics, the first steps of that great unravelling began in the deep time of the early Mesozoic as Pangea once whole began to divide. As Pangea enters the early stages of its breakup during the Triassic period, the supercontinent still spans nearly pole to pole, but internal stresses and external forces have already begun to reshape its structure. The rifting that began deep within the crust now becomes more pronounced, creating long linear fault systems and subsiding basins that fill with sediment and eventually seawater. One of the most prominent of these features forms along what will become the central Atlantic margin. Here, extension leads to the development of a wide rift zone that includes multiple parallel valleys, each bounded by faults and filled with thick sequences of sediment. These rift basins preserve a record of changing environments over time, from fluvial systems and ephemeral lakes to shallow marine incursions. The sequence of rocks deposited in these basins often shows a characteristic pattern. Coarse alluvial fan deposits at the base, followed by fluvial sandstones and mudstones, and capped by evaporates and shallow marine carbonates, marking the progressive deepening and widening of the basin as rifting continues. Volcanism becomes increasingly prominent in these zones. Large igneous provinces, or LIPs, form as vast volumes of magma rise through the thinning crust and erupt at the surface or spread laterally as intrusions. One of the most extensive of these events is the Central Atlantic Magmatic Province, or CAMP, which covers large portions of what are now eastern North America, northwestern Africa, and parts of South America and Western Europe. This enormous outpouring of basaltic lava leaves behind thick layers of igneous rock, including sheet flows, sills, and dikes. The timing of these volcanic episodes is closely tied to the rifting process, and often occurs in short, intense pulses. These events release massive quantities of volcanic gases, including carbon dioxide and sulfur dioxide, into the atmosphere. The environmental consequences are significant. In some cases, global temperatures rise sharply due to the greenhouse effect, while in others, sulfur aerosols cause short-term cooling and reduced rainfall. Fossil and geochemical records from this time show evidence of stress in both terrestrial and marine ecosystems. The End-Triassic extinction. One of the major extinction events in Earth's history coincides closely with the camp eruptions. In the oceans, many species of ammonoids, conodonts, and reef-building organisms disappear. On land, the extinction of several large reptilian groups clears ecological space for the rise of early dinosaurs, which had already begun to appear but now become more dominant. The cause of the extinction is likely multifactorial, but the rapid addition of volcanic gases to the atmosphere changes in ocean chemistry and habitat disruption due to climate shifts all contribute. These effects are recorded in the rocks as shifts in carbon isotopes, a decline in biodiversity and widespread deposits of volcanic ash and lava. As the Atlantic Ocean begins to open and widen, the once connected regions on either side slowly drift apart. Eastern North America and northwestern Africa, which once shared mountain belts, river systems, and ecosystems, now move in opposite directions. The passive continental margins that develop along these coasts become zones of thick sediment accumulation. As rivers from the interior flow toward the new ocean, they deposit vast amounts of eroded material along the continental shelves. These passive margins are marked by broad, shallow platforms that gradually descend into deeper waters. Over time, layers of sand, silt, and clay accumulate, preserving a continuous record of environmental change. Marine transgressions periodically flood these shelves, leaving behind limestone beds and fossil-rich deposits that document the expansion of shallow seas and the spread of marine life. The breakup of Pangea is not confined to the Atlantic region. Other parts of the supercontinent begin to rift and separate as well. In the south, Gondwana starts to fragment. The landmasses that will become South America, Africa, India, Antarctica, and Australia begin to move away from one another. Rifting in the southern portions of Pangea creates new basins, faults, and magmatic zones. In some areas, such as present-day southern Africa and eastern South America, rift basins form with similar sequences to those in the north. These basins become repositories for sediments and fossils that reflect local environmental conditions. In other regions, such as Antarctica and Australia, thick volcanic sequences and tectonic deformation begin to shape the margins of future continents. In the Tethyan region, between the northern and southern halves of Pangea, complex patterns of plate motion develop. The closure of the Paleotethys Ocean and the opening of the Neotethys generate subduction zones, island arcs, and accretionary wedges. These tectonic interactions eventually give rise to the mountain belts that will form parts of the Alps, the Zagros, and the Himalayas. At this stage, the processes are still in their early phases, but the movement of plates and the interaction of continental fragments already set the groundwork for future orogenic events. Microcontinents and terranes move across the Tethys, some colliding with larger landmasses, others becoming isolated. These fragments carry their own fossil records, volcanic histories, and sedimentary sequences, adding to the complexity of the future continental mosaic. Climate continues to respond to the rearrangement of land and sea. As Pangea breaks apart, new coastlines emerge, and ocean circulation patterns shift. Narrow seaways develop between rifting continents, altering the flow of currents and redistributing heat and moisture. These changes create new climate gradients and influence the distribution of rainfall, temperature, and wind. Regions that were once dry may become wetter, while others grow more arid. These shifts affect vegetation patterns, river systems, and soil development. In turn, these environmental changes influence the evolution and dispersal of organisms. Fossil floras from the Triassic and Jurassic periods show changes in species composition and distribution, reflecting the response of plants to both climate change and shifting geography. The biological consequences of Pangea's breakup continue into the Jurassic. As the continents move apart, populations become more isolated, leading to the development of distinct faunas on different landmasses. Dinosaurs diversify into a wide range of forms adapted to local environments. In some regions, large sauropods dominate the landscape, feeding on tall conifers and moving in herds across open plains. In others, smaller ornithischians and agile theropods take advantage of forested or coastal habitats. Marine reptiles expand into the newly forming seas, including ichthyosaurs, plesiosaurs, and marine crocodilians. Each continental fragment begins to develop its own evolutionary path shaped by its position, climate, and biological inheritance from the unified world of Pangea. These divergent paths are recorded in the rocks that now lie scattered across the globe. Basins in North America, Europe, South America, and Africa preserve similar sequences of rifting volcanism, sedimentation, and biological turnover. Though these rocks are now separated by vast oceans, their similarities reveal the shared origin of their host continents. The matching layers of basalt in Camp, the equivalent fossil floras of the early Mesozoic, and the parallel rift structures all confirm that these lands were once joined. The slow movement of tectonic plates has spread them apart, but their histories remain aligned in stone. By the end of the Jurassic, the separation of continents is well underway. The Atlantic Ocean has widened, the Tethys continues to evolve, and the once unified supercontinent is a memory written in geology. Yet the process of breakup is far from complete. The continents will continue to drift, collide, and reshape for hundreds of millions of years to come. The forces that once assembled Pangea now drive its disassembly in a cycle that has repeated throughout Earth's deep history, and will continue as long as the planet remains geologically active. As the Jurassic period unfolds and Pangea's breakup accelerates, the global geography becomes increasingly complex. The Atlantic Ocean, which began as a narrow rift between what are now eastern North America and northwestern Africa, continues to widen as new oceanic crust forms at the mid-Atlantic ridge. Seafloor spreading pushes the continental plates apart, and passive margins along the coasts of the drifting continents accumulate thick sequences of sediment. These layers, composed of eroded material from the newly formed continental interiors, record the changing landscapes and environmental conditions of a world in transition. Along these passive margins, broad continental shelves extend outward into the ocean, collecting the deposits of rivers, deltas, and shallow marine systems. The resulting stratigraphy reflects a combination of tectonic subsidence, eustatic sea level changes, and variations in sediment supply, creating patterns that geologists will later use to reconstruct the pace and direction of continental drift. While the Atlantic continues to open, the fragmentation of Gondwana intensifies. In the southern hemisphere, South America begins to move westward, pulling away from Africa and opening the South Atlantic Ocean. The rifting is marked by the formation of deep sedimentary basins, the intrusion of large dike swarms, and the extrusion of basalt flows, particularly in regions such as the Paraná and Itendeka plateaus. These volcanic rocks, when compared geochemically and magnetically, match across the modern Atlantic, providing further evidence of the continent's former unity. In the east, India begins its northward journey, detaching from Antarctica and moving toward the equator. This movement is slow but persistent, and in time it will lead to one of the most significant continental collisions in Earth's history. Meanwhile, Australia and Antarctica remain joined, rotating slowly as a single block, though signs of future separation are beginning to appear along their shared boundary. Tectonic activity during this time is not limited to rifting. Subduction continues along the active margins of the Pacific Basin, where oceanic plates dive beneath continental lithosphere. These convergent zones generate extensive magmatic arcs, deep ocean trenches, and mountain-building events. The western edges of North and South America remain tectonically active, with volcanic chains forming above subduction zones and terrains accreting onto the continental margins. These terrains, fragments of crust with distinct geologic histories, are transported by oceanic plates and added to the growing edges of continents. Their rock types, fossil contents, and magnetic signatures often differ sharply from the surrounding lithologies, revealing their exotic origins. The process of terrain accretion contributes to the growing width and structural complexity of continental margins, and plays a key role in the evolution of mountain belts throughout the Mesozoic. Oceanic circulation also begins to change in response to the rearrangement of continents. As the Atlantic widens and new seaways open, ocean currents reorganize, redistributing heat, salinity, and nutrients across the globe. In the Tethys Ocean, which separates the northern continents from the remnants of Gondwana, warm, shallow waters support extensive carbonate platforms, reef systems, and a diverse array of marine life. The carbonate deposits formed in these regions are rich in fossils including corals, rudists, ammonites, and foraminifera. These organisms not only form complex ecosystems, but also leave behind thick accumulations of limestone that serve as valuable paleoclimatic and paleoenvironmental archives. Variations in oxygen isotopes within these limestones allow scientists to estimate past ocean temperatures, while changes in fossil assemblages track evolutionary trends and extinction events. On land, the continued breakup of Pangea leads to further isolation of faunal populations. As continents drift apart, the once continuous corridors for animal migration are severed, leading to divergent evolutionary paths. In North America, dinosaurs such as large sauropods and bipedal theropods dominate the landscape, while in what will become Europe, insular conditions begin to influence the evolution of smaller-bodied species. South America, now becoming increasingly isolated, develops unique faunal assemblages that will later include bizarre and distinctive forms. The rise of flowering plants or angiosperms begins during this time, although they remain limited in distribution and diversity during the Jurassic. Gymnosperms, including conifers, cycads, and ginkgos, continue to dominate terrestrial ecosystems, forming extensive forests in temperate and tropical zones. The sedimentary record of the Jurassic reflects these ecological and tectonic changes. In many regions, alternating layers of sandstone, shale, and limestone accumulate in thick sequences, preserving both terrestrial and marine environments. These rocks often contain fossils of dinosaurs, marine reptiles, early mammals, and abundant invertebrates. Coal beds in some areas mark the presence of swampy lowlands, while evaporites indicate arid conditions and restricted basins. These environmental signals provide a window into the shifting climate zones of a world reorganized by plate motion. Paleosols, fossilized river systems, and dune fields reveal patterns of rainfall, vegetation, and wind, helping to reconstruct the continental interiors as they adapt to new configurations and climatic influences. As the continents continue to move, the interior of former Pangea transforms. Uplifted regions erode, supplying sediments to newly formed basins, while tectonic forces create additional deformation zones. In some areas, intraplate stresses cause reactivation of old faults, forming structures that accommodate local extension or compression. These structural features control the location of sedimentary basins, volcanic centers, and hydrothermal systems. They also influence groundwater flow, landscape development, and the preservation of fossils. Over time, these small adjustments contribute to the broader pattern of continental drift and highlight the ongoing complexity of Earth's surface dynamics. One of the key features of this period is the continuing evolution of the Atlantic basin. As seafloor spreading progresses, the magnetic signature of the newly formed crust records reversals in Earth's magnetic field. These magnetic stripes, symmetric about the mid-ocean ridge, allow geologists to determine the age of the ocean floor and the rate of plate movement. By matching these magnetic patterns with those on adjacent continents, scientists can accurately reconstruct the positions of landmasses over time. The data confirm that the Atlantic continues to widen at a steady pace, gradually separating the continents that were once united in Pangea. Meanwhile, the Pacific Basin remains the largest and most geologically active ocean on the planet. Subduction zones along its margins consume old oceanic crust and drive the formation of island arcs, back-arc basins, and extensive volcanic chains. These dynamic processes maintain the balance between crustal production at spreading ridges and crustal recycling at trenches. They also contribute to the global carbon cycle, as subducted sediments carry organic material and carbonate minerals into the mantle, where they may be stored, remobilized, or returned to the surface through volcanism. This long-term carbon exchange plays a vital role in regulating atmospheric composition and surface temperature, linking plate tectonics to climate over geological timescales. As the Jurassic progresses, Earth becomes a world of drifting continents, changing climates, evolving life, and active geology. The unity of Pangea has given way to a new phase of separation and complexity. The continents once gathered into a single mass now embark on independent trajectories that will shape the modern world. Yet in the rocks that span these separating lands, the matching sediments shared fossils, aligned structures, and mirrored magnetic patterns. The memory of their ancient union remains. These traces endure across oceans and through time, silently recording the long process of division that follows every great assembly. As the Jurassic period draws onward and the former unity of Pangea fades further into geological memory, the continents begin to assume identities more recognizable to modern observers. The breakup of the supercontinent, while gradual, is now irreversible. South America, steadily moving westward, separates further from Africa, and the South Atlantic Ocean continues to open along its spreading axis. The coastlines on either side, once part of the same tropical interior, now face each other across a widening ocean, each evolving under different tectonic and climatic influences. Along these rifted margins, passive basins grow thicker as sediments pour in from continental rivers. These sediments, layers of shale sandstone and limestone, record the erosion of ancient mountain belts, the rise and fall of sea levels, and the spread of new ecosystems that fill the niches created by drifting landmasses. India, once part of the southern reaches of Gondwana, moves northward at an accelerating pace. Although its full collision with Asia remains far in the future, the journey has already begun. Its path across the Tethys Ocean leaves a trail of seafloor behind it, rich with marine sediments, volcanic arcs, and remnants of microcontinents caught in the convergence zone. As India approaches the equator, its tropical latitude contributes to the development of humid climates and rapid vegetation growth, both of which play a role in erosion and sedimentation along its margins. To the east, Australia and Antarctica remain joined, but early signs of extension begin to appear in their shared crust. These initial movements, subtle in their beginning, mark the start of a slow and complex separation that will take tens of millions of years to complete. In the northern hemisphere, Laurasia, comprising what will become North America, Europe, and Asia, continues to evolve as a fragmented collection of drifting plates. Europe becomes increasingly separated from North America as the Atlantic widens. Shallow marine basins form across the low-lying regions of Western Europe, filled with carbonate platforms, reef systems, and lagoonal deposits. These environments, supported by warm sunlit waters, are ideal for the accumulation of marine fossils. Ammonites, belemnites, and marine reptiles leave their remains in limestone beds, while the fine muds of deeper shelves preserve delicate invertebrates, fish skeletons, and microscopic plankton. These fossils help paleontologists correlate rock layers across great distances and understand the pace of biological change during a time of continental dispersion. North America, now drifting westward, maintains an active margin along its western edge. Subduction of the Farallon plate beneath the continent drives the development of a long volcanic arc and associated mountain building. Sediments eroded from these rising highlands travel eastward into interior basins, forming thick deposits that capture the changing environments of the late Jurassic. River systems, lakes, and floodplains dominate the interior, while to the west forearc basins and accretionary complexes grow as new crust is added to the margin. These tectonic processes create a dynamic landscape, one shaped by both deposition and deformation, with a mix of volcanic activity, erosion, and sedimentation occurring side by side. Across the globe, these geological transformations continue to alter climate. The separation of continents creates new coastlines, islands, and marine corridors. Ocean currents respond to the shifting geography, circulating water masses across greater distances and distributing heat in new ways. The opening of the Atlantic, the expansion of the Tethys, and the closure of older ocean basins create a patchwork of current systems that influence temperature, salinity, and weather. Atmospheric circulation also responds. With the break in Pangea's interior, landmass moisture from the oceans penetrates farther inland. Arid zones shrink in some areas, while in others the presence of mountains and shifting wind belts enhances rain shadows and dry conditions. These climatic changes influence the distribution of vegetation, soil formation, and the behavior of rivers and lakes, all of which are recorded in the sedimentary archives that blanket the continents. The fossil record during this time reflects the biological consequences of these environmental shifts. Dinosaurs continue to dominate terrestrial ecosystems, adapting to the varied landscapes that emerge on each drifting continent. In North America and Asia, large sauropods such as Diplodocus and Mamenchisaurus graze in open woodlands, while theropods like Allosaurus and Synraptor hunt across plains and forest edges. In the southern continents, distinct lineages evolve, isolated by growing oceanic barriers. Marine reptiles become increasingly specialized, with ichthyosaurs adapting to fast swimming in open oceans, while plesiosaurs develop long necks for hunting in shallow seas. Crocodiliforms diversify into both freshwater and coastal marine environments, and turtles expand into various aquatic habitats. In the skies, early pterosaurs glide above coastlines and lagoons, feeding on fish and small prey, while the first true birds begin to appear from feathered theropod ancestors. The sedimentary rocks of the Jurassic preserve a vast amount of this life. In many regions, fossil-rich deposits form in low-energy environments such as lagoons, lake bottoms, and floodplains. These deposits often include not only bones and shells, but also impressions of skin feathers, and even behaviours such as footprints, burrows, and nesting sites. The preservation of such delicate features requires calm conditions and rapid burial, often the result of sudden floods or volcanic ashfalls. These exceptional fossil sites, known as Lagerstätten, offer rare and detailed glimpses into Jurassic ecosystems, revealing not just species diversity, but also interactions between organisms and their environments. Volcanism continues to play a central role in shaping both land and climate. In regions affected by ongoing subduction or rifting, volcanic eruptions release ash and gases into the atmosphere. These events, depending on their magnitude and duration, can cause short-term climatic cooling by blocking sunlight or contribute to long-term warming through greenhouse gas emissions. The chemical signatures of these eruptions are recorded in layers of volcanic ash that serve as time markers within sedimentary sequences. Radiometric dating of these layers allows geologists to calibrate the ages of fossils and correlate strata across continents, creating a global timeline of biological and environmental change. By the end of the Jurassic, the world has become a mosaic of drifting continents, shallow seas, growing oceans, and active mountain belts. The once unified Pangea is now a fragmented memory, its pieces scattered across the globe, each following a tectonic path set in motion by deep mantle forces. Though the separation continues, the geological and biological connections forged during the time of unity remain embedded in the crust. Rocks on opposite sides of oceans still match in composition and structure. Fossils echo a shared evolutionary history. Sediments laid down in identical environments now rest thousands of kilometers apart, yet still bear the imprint of a time when they were part of a single continuous landscape. In the slow unfolding of tectonic time, the transformation is not yet complete. The continents will drift farther, new oceans will grow wide and deep, collisions will create new mountain ranges, and subduction will destroy old seafloor. But the story of Pangea, its formation, its vast stretch across the planet, and its eventual disassembly remains a defining chapter in Earth's history. It is a story recorded not in memory, but in rock, in fossil, and in the silent architecture of the planet itself. As the Cretaceous period begins, the separation of the continental fragments that once formed Pangea continues to accelerate. The Atlantic Ocean, no longer a narrow seaway, has become a true ocean basin, with established mid-ocean ridges generating new crust and pushing the continents farther apart. South America and Africa, once connected by the vast tropical interior of western Gondwana, now lie on opposite sides of the South Atlantic. Along both margins, thick sedimentary wedges develop as rivers drain the rising interiors and deposit material into the ocean. The passive margins grow wider, subsiding under the weight of accumulating sediments and forming broad continental shelves. These sedimentary sequences preserve not only the erosional history of the continents, but also the changing composition of the atmosphere and oceans, as Earth continues to adjust to its new configuration. India, having detached from Antarctica and Australia, now moves rapidly northward across the Tethys Ocean. It carries with it a suite of Gondwanan flora and fauna, isolated from other landmasses and evolving along a distinct path. Its eventual collision with Asia is still tens of millions of years away, but even in this early stage, the Indian plate moves faster than any other continental fragment. The oceanic crust behind it stretches, forming the Indian Ocean, while the crust ahead of it begins to crumple and accumulate sediments in advance of future mountain building. The path of India's journey is recorded in seafloor magnetic anomalies and in the orientation of fracture zones, which together reveal the trajectory and speed of its movement through deep time. In the southern hemisphere, Antarctica and Australia remain loosely connected, though rifting is slowly progressing along their boundary. Evidence of this early extension is preserved in offshore sedimentary basins and volcanic provinces. These signs of future separation are subtle, involving faulting subsidence and minor magmatism, yet they mark the beginning of a process that will eventually send Australia drifting northward into tropical latitudes and leave Antarctica isolated at the southern pole, where it will become a continent of ice and wind. Meanwhile, the eastern margin of Gondwana continues to be shaped by subduction zones along the western Pacific. Here the Pacific plate plunges beneath the continental edge, producing volcanic arcs and mountain ranges in what will become New Zealand, Papua New Guinea, and the eastern edge of Australia. These active margins contrast sharply with the passive coasts along the Atlantic, reminding us that tectonic evolution is not uniform but varies from place to place, depending on the interplay of mantle dynamics, crustal strength and lithospheric boundaries. Laurasia, the northern remnant of Pangea, undergoes its own transformations. North America and Eurasia, though still loosely connected in some regions, continue to drift apart as seafloor spreading advances in the North Atlantic. Europe fragments into a series of microplates, basins and uplifts, many of which are submerged beneath shallow epicontinental seas. These seas host diverse marine ecosystems supported by warm temperatures and stable carbonate platforms. Coral reefs flourish along with rudest bivalves, which form massive reef-like structures unique to the Cretaceous. These carbonate environments are recorded in thick limestone successions that stretch across southern Europe, northern Africa and the Middle East. The deposits contain rich fossil assemblages from marine reptiles and ammonites to microscopic foraminifera that will later play a critical role in biostratigraphy and oil exploration. North America continues its westward drift, maintaining an active margin along its western edge. Subduction persists and the resulting compression uplifts new mountain ranges and creates deep foreland basins. During the mid to late Cretaceous, a vast inland sea known as the Western Interior Seaway floods much of the continent's interior. This seaway, which extends from the Gulf of Mexico to the Arctic Ocean, divides the continent into eastern and western landmasses. It supports a diverse marine fauna including large mosasaurs, plesiosaurs, sharks and fish, as well as abundant invertebrates and planktonic organisms. On land, dinosaurs continue to evolve and diversify with different assemblages on either side of the seaway, reflecting geographic isolation and environmental differences. The fossil record from this time includes iconic taxa such as Tyrannosaurus triceratops, Hadrosaurus and Ankylosaurus preserved in floodplain and coastal plain deposits that flank the inland sea. The biological consequences of Pangea's final separation are visible not just in dinosaurs and marine reptiles but also in the evolution of flowering plants. Angiosperms, which first appeared earlier in the Cretaceous, now spread rapidly across the globe. Their success is due in part to the development of enclosed seeds and specialized pollination strategies, often involving insects. As continents fragment and climates diversify, flowering plants adapt to a wide range of habitats, from coastal plains and uplands to river valleys and arid regions. Their appearance in the fossil record coincides with changes in sedimentary faces, including the increased presence of paleosols, fluvial deposits, and lake beds rich in leaf impressions, seeds, and pollen. These plants begin to reshape terrestrial ecosystems, supporting a wider variety of herbivorous animals and influencing soil formation and hydrology. Climate during the Cretaceous remains warm and relatively equable with high sea levels and no permanent polar ice caps. This greenhouse climate is supported by elevated levels of carbon dioxide, likely driven by increased seafloor spreading, large-scale volcanism, and the weathering of continental rocks. High sea levels flood continental margins and create extensive shallow seas, which enhance carbonate deposition and promote the burial of organic carbon. This burial acts as a long-term sink for atmospheric carbon dioxide, influencing global climate over tens of millions of years. In some intervals, particularly the mid-Cretaceous oceanic anoxic events occur. These are periods during which large parts of the deep ocean become depleted in oxygen, often associated with rapid volcanic activity and disruptions in ocean circulation. These anoxic events leave behind black shales rich in organic material and trace metals which later become important petroleum source rocks. The stratigraphic record of the Cretaceous reflects this complex interplay of tectonics, climate and biology. On every continent, sequences of sedimentary rocks preserve the evidence of rising and falling sea levels, shifting coastlines, migrating ecosystems, and global events such as asteroid impacts and oceanic crises. Volcanic ash beds interbedded with marine and terrestrial sediments provide time markers that link distant regions. Isotopic signatures in carbonate rocks reveal changes in ocean chemistry and temperature. Fossil assemblages record both evolutionary radiations and extinction events, capturing the pulse of life in a world that continues to transform. As the Cretaceous nears its end, the continents have largely assumed their present-day positions, though not yet their final forms. South America and Africa lie separated by a broad ocean. India is approaching the southern margin of Asia. North America has split from Europe, and Australia is beginning to move away from Antarctica. The Pacific remains a vast domain of subduction island arcs and deep trenches. The great supercontinent of Pangea, once a continuous expanse of rock and soil that stretched across the globe, now exists only in the patterns of rocks, the alignments of mountain chains, and the mirrored shapes of drifting coastlines. Yet even in separation, the legacy of Pangea persists. The fossils of identical plants and animals found on now distant continents. The matching sequences of sedimentary rocks laid down in shared environments. The structures of ancient mountain belts that begin on one continent and end on another. These remnants, scattered but still connected in geological memory, are the enduring record of Earth's most recent supercontinent, a vast experiment in tectonic unification, climate regulation, and biological exchange now preserved in stone. As the Paleogene period begins following the mass extinction at the end of the Cretaceous, the Earth's surface has fully transitioned into a new geologic era. The supercontinent Pangea, once unified and vast, is now divided into recognizable continents, each following distinct tectonic paths. Yet despite their separation, the geological and biological legacies of Pangea remain deeply imprinted on their crusts, sediments, and ecosystems. The scars of past collisions, the matching mineral belts, and the fossil assemblages that once roamed its continuous plains all serve as quiet reminders of their former connection. In the aftermath of the asteroid impact that ended the age of dinosaurs, ecosystems begin to rebuild on every continent now isolated from one another by growing oceans and evolving climates. The continents themselves, though separated, are not static. Plate motion continues. South America drifts farther west away from Africa, rotating slightly as it opens space in the South Atlantic. Its western edge, colliding with the subducting Nazca Plate, begins to crumple and uplift, forming the early Andes. This rising mountain range initiates new patterns of erosion, sedimentation, and climate along the continent's spine. Volcanism and crustal deformation shape its margins, while foreland basins to the east begin to fill with sediments eroded from the rising highlands. Over millions of years, these basins will preserve a rich fossil record of evolving mammals, birds, and flowering plants as they respond to isolation and environmental shifts. Africa, still largely equatorial, moves slowly northward toward Europe. Its northern edge, once part of the southern margin of the Tethys Ocean, begins to close the distance with the Eurasian Plate. The remnants of the Tethys shrink as subduction continues along the southern margin of Europe. Island arcs, microcontinents, and accretionary wedges accumulate while marine basins gradually disappear. The early stages of the Alpine and Himalayan orogenies begin to take form. These processes, set in motion by Pangea's fragmentation, mark the beginning of a new mountain-building cycle as the once separated plates begin to converge again. The collision of India with Asia begins in the early Paleogene, driven by the plate's rapid northward motion that had persisted since the Cretaceous. This collision initiates the slow, persistent uplift of the Himalayas and the formation of the Tibetan Plateau. The impact deforms the crust, thickens it, and drives faulting and metamorphism that will continue into the present day. This is not a single event, but a protracted convergence that produces some of the highest mountains on Earth and reshapes atmospheric circulation across much of the Eastern Hemisphere. Meanwhile, Australia, long joined to Antarctica, begins to move northward into lower latitudes. Its separation opens new ocean gateways, allowing cold currents to begin circulating around Antarctica. These currents, still weak in the early Paleogene, will grow stronger as Australia continues its journey, and as the Drake Passage opens between South America and Antarctica. The strengthening of these currents eventually isolates Antarctica, thermally contributing to the onset of glaciation on that continent later in the Cenozoic. For now, however, the climate remains warm and humid across much of the globe, a remnant of the greenhouse conditions that dominated the Cretaceous. In North America, tectonic activity continues along the western edge. Subduction persists along the Pacific margin, though changes in plate geometry lead to episodes of crustal extension and the formation of complex fault systems. The Rocky Mountains, initially uplifted in the late Cretaceous, continue to evolve as erosion exposes their cores and sediment is transported into adjacent basins. These basins preserve a continuous record of post-extinction recovery and diversification. In Europe and Asia, the remnants of the Tethyan Seaway remain active as shallow epicontinental seas that host tropical marine ecosystems. Coral reefs and carbonate platforms continue to flourish, leaving behind thick deposits of limestone and marl. Inland, the rise of new mountain belts begins to create rain shadows and alter regional climates. Sedimentary basins form in tectonically active zones and collect layers of sandstone shale and coal, preserving the fossil remains of mammals, plants and birds that adapt to the continent's changing environments. On all continents, the Paleogene becomes a time of recovery, experimentation and radiation. Mammals diversify rapidly, filling ecological niches left vacant by the extinction of dinosaurs. Primates, ungulates, carnivores and early rodents appear in the fossil record, each adapting to regional environments, shaped by the positions and movements of the continents. Plant life responds as well, with angiosperms expanding their dominance across nearly all biomes. Tropical forests spread across equatorial regions, while grasslands begin to take hold in drier, more open areas. The separation of continents, a legacy of Pangea's disassembly, creates barriers to migration and fosters endemism. South America, isolated for much of the Paleogene, develops its own unique mammalian fauna, including early sloths, armadillo-like creatures, and predatory marsupials. Africa, likewise separated by marine barriers, fosters the evolution of elephants, hyraxes, and early anthropoid primates. These divergent evolutionary paths are later modified by episodic connections through land bridges and island arcs, which allow selective migrations and exchanges. These rare connections, such as the Bering Land Bridge between Asia and North America, or temporary links between Africa and Eurasia, leave distinct signatures in the fossil record and in the composition of modern faunas. Throughout the Paleogene, climate remains one of the most dynamic components of Earth's system. Fluctuations in atmospheric carbon dioxide, orbital variations, and tectonic rearrangements produce alternating intervals of warming and cooling. One of the most pronounced events occurs at the Paleocene-Eocene thermal maximum, when a sudden release of carbon into the atmosphere causes rapid global warming, ocean acidification, and biotic turnover. This event, preserved in isotopic signatures and fossil assemblages, underscores the sensitivity of Earth systems to carbon cycle disruptions. In the later part of the Paleogene, as the continents continue to drift toward modern configurations, the early establishment of oceanic circulation patterns begins to reshape climate more permanently. The closure of shallow seaways, the opening of new oceanic gateways, and the development of high-latitude currents all contribute to long-term cooling trends. Antarctica, still free of permanent ice in the early Paleogene, begins to cool more significantly as cold currents and wind systems develop around its margins. This cooling sets the stage for the onset of large-scale glaciation in the next epoch. By the end of the Paleogene, the legacy of Pangea's existence and breakup is visible across every continent and ocean. The positions of the land masses reflect the cumulative motion that began with the rifting of the supercontinent. The coastlines of South America and Africa still mirror each other across the Atlantic. The sedimentary rocks of former rift valleys now lie exposed in eroded basins. The sutures that once marked continental collisions remain visible as mountain belts and fault zones. The fossils of identical organisms in once connected continents bear witness to the shared past. Even the atmospheric and oceanic systems that now shape climate and weather patterns are consequences of a world rearranged by the slow, relentless movement of tectonic plates. The story of Pangea is no longer one of assembly or unity, but of separation and divergence. The continents now distinct continue to evolve in response to their inherited structures, their new environments, and the deep processes that continue beneath their surfaces. Though Pangea no longer exists as a single landmass, it endures in the geology of every continent and in the patterns of life that once flowed across its uninterrupted expanse. As the Neogene period begins, the Earth's continents have moved into positions that resemble their modern configuration, yet tectonic activity continues to reshape their boundaries and uplift their interiors. The long process that began with the breakup of Pangea enters a new phase defined not by fragmentation, but by convergence and orogenesis. The continents no longer drift aimlessly. Many are on collision courses that will produce the mountain belts and active margins familiar today. India's collision with Asia, which began during the Paleogene, now intensifies. The Indian plate continues to push northward, driving the Himalayas ever higher and causing the Tibetan plateau to uplift and spread outward under its own weight. This ongoing collision is one of the most significant geologic events of the Cenozoic era, and it fundamentally alters global climate and atmospheric circulation. As the Tibetan plateau rises, it affects the strength and pattern of the Asian monsoon, drawing warm, moist air inland during summer and creating intense seasonal rains that shape the landscapes of South and Southeast Asia. Meanwhile, the closure of the Tethys Ocean continues as Africa approaches Europe. The Neogene witnesses the final stages of the Alpine orogeny, as the African plate pushes against southern Europe, folding and faulting crust into mountain chains such as the Alps, the Apennines, and the Carpathians. These mountains, like those formed in earlier collisions, are composed of complex assemblages of thrust sheets, metamorphic rocks, and marine sediments that once lay beneath the Tethys seafloor. Uplift and erosion expose these rocks at the surface, where they become part of the evolving topography of the continent. Inland basins formed through flexure of the crust fill with sediments eroded from the rising highlands. These basins record both the tectonic and climatic history of the region, preserving fossils of Neogene mammals' pollen from changing vegetation and the evidence of repeated glacial and interglacial cycles. In the Western Hemisphere, South America continues its collision with the oceanic Nazca Plate, driving the uplift of the Andes to even greater elevations. The mountain chain, which began forming in the late Cretaceous, now becomes a major continental divide, influencing the direction of river systems, the distribution of rainfall, and the evolution of ecosystems. To the east of the Andes, foreland basins expand and deepen, collecting sediments transported by newly formed river networks, including the ancestors of the modern Amazon and Paraná rivers. The uplift of the Andes also contributes to the establishment of new climatic regimes across South America. The mountains intercept moist air masses from the Atlantic, creating lush cloud forests on their eastern slopes and rain shadows to the west. These contrasting environments foster high rates of speciation and endemism, particularly in the tropical regions adjacent to the mountains. North America remains tectonically active along its western edge, where subduction, strike-slip faulting, and crustal extension shape the landscape. The San Andreas Fault System, which emerges as a major boundary between the Pacific and North American plates, becomes a defining feature of the western margin. This transform boundary accommodates lateral motion between the plates, producing frequent earthquakes and reshaping the coastline. In the interior, the Basin and Range Province continues to extend, forming a series of alternating mountain ranges and valleys. This extensional regime reflects the complex interactions between plate motion, mantle upwelling, and crustal thinning. These dynamic processes generate basins that trap sediments, and water-forming closed drainage systems and playas that record episodic wet and dry periods. In Africa, tectonic activity shifts from convergence to rifting. The East African rift system begins to open as the African plate starts to split into separate subplates. This continental rifting, which will eventually lead to the formation of a new ocean basin, is marked by deep fault-bounded valleys, volcanic activity, and uplifted plateaus. The rift system stretches from the Red Sea southward through Ethiopia, Kenya, Tanzania, and into Mozambique. Along this corridor, numerous volcanoes rise, including Mount Kilimanjaro and Mount Kenya. Lakes form in the rift's low points, creating unique ecosystems that support both aquatic and terrestrial life. The sediments that accumulate in rift basins preserve detailed records of climatic change, faunal evolution, and early hominin activity. Fossils of early human ancestors such as Australopithecus and Homo habilis are found in these deposits, offering critical insight into the origins of modern humans within the broader context of Africa's tectonic and environmental evolution. Antarctica, once connected to other southern continents, is now fully isolated by the opening of the Drake Passage and the deepening of the Tasman Gateway. These oceanic openings allow the Antarctic circumpolar current to flow unimpeded around the continent, thermally isolating it from warmer waters. As a result, Antarctica cools significantly, and ice sheets begin to expand across its surface. By the mid-Neogene, permanent ice covers much of the continent, initiating a major shift in global climate. The growth of the Antarctic ice sheet lowers sea levels and alters ocean salinity and circulation. Glaciation also begins to spread across the high latitudes of the northern hemisphere during the later Neogene, influenced by the rise of mountain ranges, changes in atmospheric carbon dioxide, and variations in Earth's orbit. These glacial episodes, which alternate with warmer interglacials, begin to define a new climatic rhythm that will become dominant in the Pleistocene. Australia, drifting northward, approaches the tropical latitudes and begins to collide with the island arcs of Southeast Asia. This convergence results in complex deformation along its northern margin, including the formation of submarine trenches, volcanic arcs, and forearc basins. The motion of the Australian plate compresses sediments, builds mountain belts in Papua New Guinea and eastern Indonesia, and reshapes the shallow marine platforms that connect the islands. At the same time, Australia's interior becomes increasingly arid as its movement into subtropical latitudes reduces rainfall. The centre of the continent transforms into desert and savanna environments that persist into the modern day and influence the evolution of its unique flora and fauna. In the oceans, the ongoing rearrangement of continents and seafloor spreading alters circulation patterns and nutrient distribution. Upwelling zones form along western continental margins, bringing cold, nutrient-rich waters to the surface and supporting productive fisheries. Ocean gateways open and close, modifying the exchange of water between basins and influencing the global climate system. Marine sediments record these changes in the form of microfossils, isotopic signatures, and sedimentary facies that document fluctuations in temperature, productivity, and sea level. These oceanic records complement those on land, providing a global framework for understanding the Neogene as a time of continued tectonic adjustment, climatic fluctuation, and biotic evolution. As the Neogene comes to a close, the Earth stands transformed. The continents once joined as a single supercontinent are now distinct but still influenced by the legacy of their shared past. The positions of mountain ranges, the structure of passive and active margins, and the shapes of ocean basins are all products of Pangea's assembly and disassembly. The tectonic forces that drove its formation continue to operate, guiding the evolution of the surface in new directions. The landscapes of the present mountains, plains, deserts, and coasts carry the signatures of ancient movements. Even as new events unfold, the memory of Pangea remains embedded in stone. As the Earth moves into the Quaternary period, the most recent chapter in geological time, the continents have largely reached their modern positions. The legacy of Pangea is now expressed not through visible connections, but through the deep structures beneath mountains, the mirrored coastlines of once joined continents, and the biological distribution shaped by ancient migrations and separations. The planet's surface appears settled, but the processes that broke Pangea apart continue. Plate boundaries remain active and tectonic motion subtly shifts the shape of continents and ocean basins with each passing year. At the same time, a new force becomes dominant in shaping the surface of the Earth ice. Glacial cycles driven by subtle variations in Earth's orbit and axial tilt now play a central role in global climate. Large continental ice sheets advance and retreat across the Northern Hemisphere. North America, Northern Europe, and parts of Northern Asia are repeatedly covered by thick ice that scrapes the bedrock, scours the landscape, and transports sediment over long distances. The growth of ice lowers global sea level by over 100 meters at times, exposing continental shelves and land bridges that allow species including humans to migrate across previously impassable barriers. These glacial cycles are superimposed on the geography created by Pangea's breakup. Mountain ranges formed during the assembly, and later collisions now influence the distribution and behavior of ice sheets. The Alps, the Himalayas, the Rockies, and the Andes, all born from the convergence of plates that once separated or collided, following Pangea's fragmentation, now act as climatic boundaries, guiding the flow of glaciers and shaping regional precipitation patterns. Glaciation in the southern hemisphere, though less extensive, occurs in high-altitude regions such as Patagonia, the southern Alps of New Zealand, and parts of Antarctica, which remains fully glaciated due to its polar position and the isolation imposed by the Antarctic circumpolar current. As glaciers grind across the continents, they carve out U-shaped valleys, create fjords, and leave behind moraines and outwash plains. When they melt during interglacial periods, massive volumes of fresh water enter the oceans, raising sea levels and altering salinity. These fluctuations in sea level repeatedly flood and expose low-lying coastal regions, affecting ecosystems, human migration, and sedimentary deposition. The sedimentary record along continental margins reflects these changes with alternating marine and terrestrial deposits that capture the rhythmic pulse of the Ice Age world. Meanwhile, tectonic activity continues along plate boundaries inherited from the earlier stages of Pangea's breakup. The Himalayas continue to rise as India presses into Asia. Earthquakes mark the ongoing stress along the collision zone, and rivers such as the Ganges and the Brahmaputra carry vast amounts of sediment from the high peaks to the plains and deltas below. In western North America, the San Andreas fault system accommodates lateral motion between the Pacific and North American plates, producing frequent seismic activity. In the Pacific Basin, subduction zones remain active, generating volcanic arcs, deep-sea trenches, and island chains. These features are all part of the global plate circuit that links back to the ancient mid-ocean ridges and subduction zones that once encircled Pangea. Africa's slow journey northward continues, driving ongoing collision and crustal deformation along the Mediterranean margin. In some areas, subduction zones develop where remnants of the Tethys Ocean are consumed, creating earthquakes, volcanoes, and uplifted terrains. The Alpine Apennine and Hellenic arcs evolve further, shaped by complex interactions between African and Eurasian crust. Sedimentary basins that formed as the Tethys closed are now sites of uplift erosion and human habitation. The geological record preserved within these basins, from marine fossils to terrestrial soils, reflects the environmental transitions that accompanied both tectonic convergence and climatic oscillation. Australia, firmly separated from Antarctica, moves steadily northward into the tropical belt, where it collides with the complex island arc systems of Southeast Asia. This collision zone is marked by active volcanism, seismic activity, and crustal shortening. New mountain ranges begin to rise along New Guinea and parts of Indonesia. The northern coast of Australia experiences deformation and uplift, while inland areas remain tectonically stable but climatically dynamic. As Australia's interior becomes increasingly arid, wind-blown sediments form extensive dune fields and desert landscapes, preserving a sedimentary record of climatic extremes and episodic lake formation. South America, still dominated by the Andean mountain belt, continues to interact with the subducting Nazca Plate. This interaction drives volcanic activity and crustal uplift along the western margin, contributing to high-altitude ecosystems that host specialized plant and animal life. East of the Andes, the Amazon basin, once a shallow inland sea during earlier geological periods, remains a massive low-gradient river system that drains much of the continent. The Amazon and other rivers carry sediment from the Andes to the Atlantic Ocean, building vast deltas and influencing the global carbon cycle by transporting organic matter and nutrients to the sea. Across the globe, the Quaternary period also witnesses the evolution and spread of humans. Anatomically, modern humans originating in Africa begin to migrate across the continents during glacial low stands, when sea levels are reduced and land bridges are exposed. These migrations follow paths shaped by the geography left behind by Pangea's disassembly. The Bering Land Bridge connects Asia and North America. The narrowing of the Red Sea and the presence of the Sinai Peninsula allow passage into the Levant. Island arcs and continental shelves assist the spread of humans into Southeast Asia and Oceania. Each continent presents different challenges and resources, from the mountain chains of Eurasia to the deserts of Australia and the tropical forests of the Americas. The landforms encountered by early humans, mountains, basins, plains, are products of long tectonic histories rooted in the assembly and dispersal of Pangea. As humans spread, they begin to modify their environments in increasingly profound ways. Agriculture emerges in river valleys shaped by tectonic subsidence and glacial retreat. Settlements grow in basins formed by faulting or erosion. Resources such as minerals, fossil fuels, and groundwater are extracted from sedimentary basins and mountain belts that were formed by the processes that created and dismantled Pangea. The soils in which crops grow are often derived from volcanic ash or glacial deposits. The fresh water that sustains civilizations flows along paths determined by ancient tectonic boundaries and post-glacial topography. Even in the present day, the imprint of Pangea remains visible not just in geology, but in the spatial logic of the planet. The Atlantic Ocean, still widening, preserves the symmetry of mid-ocean ridges and matching continental shelves. The oldest oceanic crust, though no older than the Jurassic, outlines the timeline of separation. Seismic activity maps the plate boundaries where continental fragments interact. Geochemical signatures trace magmas to their mantle, origins influenced by the structures inherited from Pangea's fragmentation. The continents continue to move, and the cycle of supercontinent formation and breakup is expected to continue into the future. Geologists refer to this long-term process as the supercontinent cycle. a rhythm of convergence and divergence that has occurred many times in Earth's history. Pangea was not the first supercontinent, nor will it be the last, but it remains the most recent and best studied its legacy, woven into every continent, ocean and living system on Earth. In the present geological moment, the tectonic legacy of Pangea continues to unfold in slow and deliberate motion. Though the supercontinent itself vanished over 150 million years ago, its influence persists in every corner of the planet. The continents now scattered across the globe remain bound by ancient sutures, former rift zones, and inherited weaknesses in the lithosphere that continue to guide their behavior. These inherited structures control the locations of modern fault systems, volcanic arcs, sedimentary basins, and even mountain chains still in the process of rising or eroding. Each continent bears visible and invisible traces of its former life within the supercontinent, written in patterns of rocks, fossil distributions, magnetic signatures, and seismic activity. The Atlantic Ocean, wide and deep, continues to expand along its mid-ocean ridge. The seafloor there is created from mantle material rising through a long fracture system, solidifying and moving outward on either side. This process, called seafloor spreading, pushes the Americas westward and Europe and Africa eastward at a rate of a few centimeters per year. The oldest parts of the Atlantic basin near the margins of South America and Africa date back to the Jurassic period shortly after Pangea began to rift. These oceanic plates are gradually recycled at subduction zones elsewhere in the world, part of the continuous cycle of creation and destruction that defines plate tectonics. To the west of South America, the Nazca Plate continues to subduct beneath the continent's margin, forcing the Andes Mountains ever higher and producing powerful earthquakes and volcanic activity. These geological forces not only shape the landscape but also affect climate and ecosystems, determining where rain falls, where rivers flow, and where species can live and migrate. To the east, the interior of the continent, once joined to Africa, contains sedimentary basins and cratonic shields that preserve the ancient roots of Gondwana and the Pangean core. Similar features are found across Africa, where cratons like the Congo and Kalahari remain tectonically stable, but rifting continues in the east. The East African rift, still in its early stages, is slowly splitting the continent apart along a line of deep faults and active volcanoes. If the process continues over millions of years, a new ocean will open between eastern and western Africa, repeating on a smaller scale the pattern that once split Pangea itself. In Asia, the Himalayas remain among the youngest and tallest mountains on Earth, driven upward by the ongoing collision between the Indian Plate and the Eurasian Plate. This process began during the Eocene epoch and continues today with measurable uplift, crustal, thickening, and seismic activity recorded annually. The Tibetan Plateau, which formed from the compression and buckling of the continental crust, exerts a powerful influence on atmospheric circulation. It contributes to the strength and variability of the Asian monsoon, a climate system that supports billions of people and shapes agricultural patterns across the region. The formation of these mountains would not have been possible without the earlier tectonic rearrangements triggered by Pangea's breakup. Without the initial rifting of Gondwana and the isolation and northward drift of India, the dramatic convergence that formed the Himalayas could never have occurred. In North America, the legacy of Pangea is recorded not only in the rocks of the Appalachian Mountains, an ancient orogeny formed during the assembly of the supercontinent, but also in the structure of the continental crust. Passive margins along the eastern seaboard reflect the rifting that initiated the Atlantic, with buried basins and fault systems still visible in seismic surveys. To the west, the active margin shaped by subduction transform. Faulting and crustal extension continues to produce earthquakes, volcanism, and uplift. The Sierra Nevada and Cascade ranges rise along these tectonic boundaries, shaped by processes inherited from older plate configurations that began with Pangea's fragmentation. In the Arctic, the opening of the Labrador Sea and Baffin Bay also reflects the progressive separation of plates and the formation of new ocean basins. These features, though smaller in scale, continue the same pattern of divergence, spreading and rifting that began with the supercontinent's initial break. In Europe, the remnants of the Tethys Ocean lie folded and thrust into mountain belts across the continent's southern margin. The Alps Carpathians and Dinarides record the complex history of convergence between Africa and Eurasia, shaped by subduction collision and crustal shortening. These mountains rise from the closure of ocean basins that once separated fragments of Gondwana and Laurasia. Today the region remains tectonically active, with earthquakes, slow crustal deformation, and ongoing uplift continuing to reshape the terrain. The Mediterranean Sea, a remnant of the Tethys, is shrinking as Africa presses northward. Eventually, in geological time, it may close entirely, and a new mountain belt may rise in its place, continuing the long cycle of ocean closure and continental assembly. Even Antarctica, isolated at the southern pole, tells the story of Pangea. Once connected to Australia, Africa, South America and India, it was a central part of Gondwana and the southern half of the supercontinent. As the continents drifted apart, Antarctica moved southward, eventually becoming encircled by the Southern Ocean. The opening of the Drake Passage and the Tasman Gateway allowed the Antarctic circumpolar current to form, thermally isolating the continent and allowing thick ice sheets to develop. These ice sheets, which cover most of the continent today, contain within them air bubbles, dust and chemical signatures that provide detailed records of climate over hundreds of thousands of years. Beneath the ice, sedimentary basins and volcanic provinces preserve the tectonic history of the continent, much of it shaped by processes set in motion during the fragmentation of Pangea. The movement of the continents, driven by deep mantle convection and plate interactions, is not finished. Models of future plate motion suggest that the Atlantic Ocean may continue to widen, while the Pacific slowly closes. Subduction zones around the Pacific basin are expected to persist, gradually drawing continents together into new configurations. Over the next several 100 million years, a new supercontinent may assemble. Whether this future landmass forms where Pangea once stood, or somewhere entirely new, remains uncertain. The cycle of supercontinent assembly and breakup, known as the Wilson cycle, has occurred multiple times in Earth's history, and Pangea is simply the latest example. It was preceded by Rodinia, which existed over 1 billion years ago, and by Nuna before that. Each supercontinent has left behind its own geological fingerprint, and each has helped drive long-term changes in climate, sea level and biodiversity. The story of Pangea is not just a story of a landmass, but of the processes that shape planets. It is the story of mantle heat rising and falling, of crust colliding and separating, of rocks folding, melting and reforming. It is the story of ancient oceans closing and new ones opening, of mountain belts rising and eroding away, and of ecosystems adapting to the shifting contours of a restless Earth. Though Pangea has long since vanished, it continues to live on in the structure of the continents, the patterns of life, and the ongoing motion beneath our feet. Every earthquake, every volcano, every shifting coastline is a continuation of the same deep process that once brought all land together into one and then scattered it again across the face of the globe.